this is a table similar to what you had in the practice from day 5 here. But here we're just looking at the points themselves. So I wanna work through this a little bit here. This is one of the problems from the practice in your book that I just felt would be good for us to go through together. It says here B and D are stationary points, and C is a point of inflection. Anytime you see those terms, you got to write down what that means, okay? Stationary point means what?
Critical value.
Critical value, which means what?
F prime is 0.
F prime is 0, okay? C is a point of inflection, so what does that mean?
F double prime is 0.
Yeah, F double prime is 0, okay? So, automatically, that's one of the things I want you guys to get used to doing. Anytime you hear these terms, this is the kind of stuff that needs to pop into your head. Alright? When you hear stationary point or critical value or max or min, you ought to automatically be thinking, first derivative equals 0. When you hear point of inflection or a change in concavity, something like that, you ought to be thinking, second derivative equals 0. Okay? So now let's look at the different things that we have here. First of all, with the original function. The original function is simply our position. Are we above or below the x-axis, or are we on the x-axis? That's what the positives and negatives tell us. So at A, obviously we're above the x-axis. At B, we are below, so that's negative. At C, we are above. At D, we're above. And at E, we are on 0, on the x-axis. Okay? Now, let's think about our first derivative. Okay? The first derivative is telling us whether we are what or what?
Increasing or decreasing.
Increasing or decreasing. Okay? So at A, what are we doing?
Decreasing.
We're decreasing, so F prime is?
Negative.
Negative. Okay? What? Okay. At B, we were already told this is a stationary point, so we know that at B, the first derivative is 0. At C, what's going on there? It's increasing, so it is positive. At D, it equals 0 again, because we were told that's a stationary point. And then how about at E? It's negative. Our function is decreasing again. Okay? So, you have the second derivative. Now we're talking about concavity. Alright, which one of these were we already told? C. At C, we know it's 0. Okay, so this right here is our point of inflection. Alright, so to the left of it, are we concave up or concave down?
No.
We're concave up. Alright? Concave up, kind of looks like a cup. Alright? So that means our second derivative is?
Positive.
Positive. Alright, so at A and at B, it's positive. Okay, concave down looks like a frown. Alright, so at D and E, our second derivative is? Negative. Okay? Now, it's not always going to be quite that obvious, especially if you look right in here around C. I mean, if you look at this, you're like, how is that concave down? I don't really see anything. Well, that's because it's just barely started to slow down. Alright? It hasn't really started to slow down noticeably yet until we're starting to get up here. Now we see, oh yeah, it's definitely slowing down, and now it's slowing down so much we're going in the opposite direction. okay? You can kind of think of it like your speed if you've ever ridden a bike, okay? You go down a hill, you're speeding up, speeding up, speeding up, speeding up, speeding up, going faster and faster down a hill, okay? And that road is concave up because you're going up the other side of the hill, but at some point your momentum kind of dies and you start to slow down.
And then gravity takes you down back.
And then gravity slows you down and slows you down and slows you down, and unless you pedal really, really hard, then you start rolling backwards. And that happens right around here.
So we just knew that C is 0 in the second derivative because it says it's a point of...
It tells us that, yes. Okay? So the turning points of the function would be where? B and D, okay? The turning points are B and D. Alright, B is a min point on a part where it's concave up, okay? So B is a minimum point, but we are currently accelerating at that moment, alright? D is a max point, and we're actually slowing down, or the acceleration is negative at that point, okay? And then the inflection point, we're changing from concave up to concave down on a portion of the graph that is increasing. Okay, so that's one way we can describe that. Okay? Any questions here? All right. Later on, we're going to look at ones where we actually have specific values, and we'll look at the actual sign diagrams for each of these side by side and be able to kind of break them up and look at parts that make a little bit, we can tell a lot about what's going on the graph by looking at the three sign diagrams side by side. Okay? All right. So, earlier when we were talking about max and min points, we said that there were two ways to prove that a point is a max or a min point. Okay? The first step in this whole process was to prove that its x value was at a critical value. Okay, so you took the first derivative, set it equal to 0, and like here, do we get negative 7/5 to give us 0 on our derivative? Okay, if that's not true, then we can automatically say, no, there is not a local min at this point. Okay? But then the next part of that, I told you you had two options for. You either had to show that there was a change in sign from either negative to positive or positive to negative on the derivative, or you could use the second derivative test. Okay? Let's look at what the second derivative test says. Alright? To prove whether a critical point is a min or a max point or a point of inflection, if the derivative equals 0 at C, then C will yield one of those three things. It'll be a relative maximum if the second derivative is negative at C, because that means that it is concave down, so you have a max point. Okay? That's how you're getting a max point. It's going to be concave down. You're going to have a relative min point if the second derivative is positive. Okay? Because it's opening like this. You're going to have a minimum value there. Okay? And then, this is what I was telling you before. If you have f prime is 0 and f double prime is 0, you have a plateau point. And that's also a point of inflection. Okay? So, the second derivative test, this will identify all plateau points are points of inflection. The converse of this is not true. Not all points of inflection are plateau points, okay, as we saw in the previous cubic function, okay? So, we'll finish real fast with this, okay? So we have f prime equal to this. So f double prime of x is 15x squared plus 14x minus 5, right? Notice you were given f prime, not the original function, okay? So what do I have to do to show that there is a local min here?
Set equals
Set
to
to
0.
0. Or set f prime x equal to 0 and then f double prime x has to be negative. Or positive.
It would have to be positive, okay? So here's the thing. We have to check two things. Is f prime of negative 7/5 equal to 0? So notice we're just plugging it in. And then secondly, is f double prime of a negative 7/5? To be a min point, it's got to be greater than 0. We have to be concave up. So you notice this is a pretty simple process. We actually don't have to find the other critical values. This is where this is really nice. Okay? To do it with what we call the first derivative test, or the way that we were doing it just by looking for changes in sign, we would have had to find all the other critical values and then figure out our sign diagram and then look for changes from decreasing to increasing to determine a local min. Here, I don't care about what the other critical values are. All I want is it a local min? So I plug it in to f prime, and it does equal 0. I plug it into f double prime, and when I plug in a negative 7/5 into f double prime, I do get a positive value, because 15 times that squared is a whole lot bigger than 14 times that. And even if I subtract another 5, I'm still going to end up positive. So that is correct. So therefore, and obviously you would show all the work, but that's how we can prove it. And that's where the second derivative test is really nice. Okay?